So welcome to the afternoon session. I already teased it a little bit in the morning. So this talk is maybe, not so much about showing reductions, but rather proving that sometimes you can find barriers towards which would rule out hardness reductions in the fine-grained sense. So let me start with this picture. First of all, I think you should, kind of be proud of yourselves. This is what you've learned so far. I think I squeezed all of them in there. Maybe there's more. Maybe from today's exercise sheet, I wasn't sure whether I should spoil it. OK. Good. So yeah, the big question, which I put at the very top here, is one conjecture to rule them all. Because we had 3 days plus today, in which we studied 3 different conjectures: 3-sum, APSP, and then SETH. So maybe also you could regard OV as like one of the base hypotheses. And really what we came up with is 3 chunks of problems which are 3-sum, APSP, or SETH hard, with maybe a couple of very few exceptions which might be hard under 2 different hypotheses. But nevertheless, like to understand the complexity of polynomial time problems, it seems that we have to assume 3 different hypotheses. And wouldn't it be much cooler if there was just one hypothesis? So maybe 3-sum and APSP could actually be implied by SETH. That would simplify the state of affairs a lot, because you really only have to believe in SETH then. So does SETH imply the 3-sum or APSP hypothesis? This is the question which we would like to ask. And today, as I've said, we'll show that most likely not, or at least, I'm being very optimistic here, but there's reasons to believe that this might not be the case. So what's a very generic approach towards proving that you cannot show hardness reduction, right? There's like a double negative in here. So the very abstract idea is this. You find some property P which holds for 3-sum, which does not hold for set, and you show that it is preserved by fine-grained reductions. Okay? If we could find such a property, we would rule out a reduction from SET, like from SUD to 3-sum. Yeah, I guess I wanted to ask you what this property could be, but then I've already spoiled it in the title. So, OK, so the property which we'll investigate is having a fast non-deterministic or co-non-deterministic algorithm. A priori, it doesn't have to make sense. I'll define it in the next slide. But this is an interesting property. And interestingly, this is not the only property which the fine-grained community and friends have identified. Turns out there has been work very recently, actually, also on some other sort of area, which is to say that the problem admits a certain polynomial formulation, whatever that means. And even also that can be used to say that maybe there should not be hardness reductions from SETH to some problems. Yeah, but today's focus really is on the fast co-non-deterministic algorithms. So a quick show of hands, who of you is familiar with like the concept of NP and co-NP, non-determinism, co-non-determinism, that sort of stuff? OK. I'll nevertheless show you some definitions. Let's focus on decision problems first. And let me properly define what it means to have a non-deterministic algorithm for a decision problem. So instead of, like in a normal algorithm, right, you have an input and you produce an output, whatever is the appropriate answer to your problem P. This time we get 2 inputs. We get an instance of our problem and a proof, that be known by pi. And the output is, well, yes or no, depending on the problem. But you have the following 2 properties. If x is a yes instance, then there must be a proof such that the algorithm returns yes. And on the other hand, if x is a no instance, then for all proofs, the algorithm cannot be fooled. So it would actually output no. Right? Looks extremely familiar, because this is exactly what we did in the morning. This is just Merlin. Merlin was non-determinism. OK, now questions about this? Good. Co-non-determinism is just the same thing for the complement problem. Right? So you have a co-non-deterministic algorithm for your decision problem if you have a non-deterministic algorithm for the complement problem, which is you flip the answers yes and no. So in other words, it would say something like, if you get a proof for the no case, And if you are no instance, then there exists a proof for which the algorithm definitely says no. And on the other hand, if you're in the yes case, then for all proofs, the algorithm will definitely say yes. It's like exactly the complement from up there. But don't worry too much about it. Just stick with the definition algorithm for the complement problem. And I also like to define the term verifier, which is just if you have a non-deterministic and a co-non-deterministic algorithm. Which basically says whatever instance you give me, or whatever instance I give you, along with a proof, you'll be able to verify its answer to me. Okay? One more technical definition before we get to the fun stuff. This is a little bit restrictive because it's about decision problems. This, I think, is mainly because the guys who came up with this paper, with this barrier, were maybe inspired by complexity theory, but actually, we also have a bunch of problems which are not decision problems, like finding a negative triangle, finding a path in a graph or something. Also for these problems, it makes sense to come up with to think of verifiers. And one reasonable definition, for instance, this time still you're given an instance of your problem and a proof. The algorithm outputs either an answer to your problem or some sort of trash symbol, like bottom. Okay? Then the properties is, the completeness property is there is one proof such that the algorithm returns the correct answer. In particular, it does not return the trash symbol. And on the other hand, the soundness is for no matter what proof we provide, the algorithm will never produce a wrong answer. It might produce bottom, but it will not produce a wrong answer. Okay? This is like a verifier for non-decision problems. Okay, so let's try and work with this. This is the property which we want now was we have a fast verifier. But for this to make sense, we have to show that this property does not hold for SAT. And of course, this is like a ridiculous statement. We cannot even prove, we can't prove any sort of lower bound, so we kind of have to assume it. And this assumption is called the non-deterministic strong exponential time hypothesis, or NSET. Okay, so it's another strengthening of SATH. And the statement formally is the following. For each epsilon, there is some k greater than 3, such that there is no, well now, co-non-deterministic algorithm for KSAT running in time 2 to the 1 minus epsilon n. So basically it says SATH even holds when you're allowed to use co-non-determinism. Why did I not put non-determinism here? Can anyone see that? Sorry? Yes, exactly. Like non-deterministically, SAT is extremely simple. What's the algorithm? Okay, everyone saw it. You guessed the satisfying assignment. Exactly. This is your proof. Good. Still, yes?
Are there like non-trivial co-non-deterministic algorithms?
Not that I know. There's a lot of proof systems which do something, right? But there's no proof system which unconditionally is better than 2 to the n. Which would basically refute the hypothesis if it really existed.
No, it won't, right? For example, something like what we described for SAT, like a co-non-deterministic algorithm.
Oh, I see. You mean like for bounded k? I don't know. Sorry.
Like 3 SAT.
I don't know.
What's the question?
Is there a non-trivial proof system for KSAT? I mean, obviously, what you can always for fixed KSAT better than 2 to the n. There was
Like 2 to the n minus n over k.
right. I mean, obviously, yes. Like obviously, you can. That obviously
Yeah,
exactly.
like using the witness, can you improve?
Yes. No. So I'm not aware of anything which non-trivially uses co-non-determinism to do something. But also, I'm not for proof complexity. Sorry. But one question which is particularly important in the context of fine-grained complexity, especially that in the recent years, actually, we came up with more and more hypotheses. It becomes important to argue that they're plausible. And this one really, might not seem plausible at all because really it gives you so much power on determinism. But still, there's a couple of reasons why this might be believable. The first one is this is really the fine-grained analog of NP versus co-NP. NP not equal to co-NP. And in the NP hardness world, this is actually used very similarly as a barrier. If you have a problem for which you believe maybe that it's not NP complete, one way of gathering evidence for that is you prove that the problem is in NP intersect co-NP. Then we do not expect the problem to be NP complete because otherwise it would refute this conjecture. Okay, so this is like the fine-grained, when SETH is the fine-grained analog of P not equal to NP, NSAT is the fine-grained analog of NP not equal to cone. Next, and this is already like targeted towards the question, there has been extensive research not only on SAT algorithms, but on something like proof systems. You know, proof system is basically something like an algorithm, but instead of caring about running time, you really care about like what is the smallest proof you can write down, maybe with some restricted rules that would certify that a given formula is not satisfiable. Often they phrase it the other way around. Often they say that you can prove that something is a tautology. Same thing. And the third reason is, well, if you falsify NSAT, then you get some circuit lower bounds. This is actually the same as for SETH. I'm not sure whether we ever explicitly mentioned it, but one reason why we believe in SETH is that if you would falsify it, it would imply some breakthroughs in circuit complexity. Good. So let's assume NSAT for now. What does it give us? We still have to check that this property, having a fast verifier, is preserved by fine-grained reductions. Otherwise, the barrier is worth nothing, right? So what we kind of have to say is, suppose that you have a problem P, and you have a fine-grained reduction from P to the problem Q with the appropriate running time. So if P has a conjectured running time of n to the A, then you have fine-grained reduction from A to B such that Q has a conjectured running time of Q to the B. So it's a tight reduction. That's all I want to say. And now you suppose that there's a verifier for Q which runs in non-trivially fast, so time n to the B minus epsilon for some epsilon. Then, well, it's very easy to see that now you get a verifier for P, which is faster than n to the A for some epsilon. Okay, can you see how? The reduction is deterministic, let's say, yes.
So that's why.
Good, yes. So can you be a little bit more explicit? What do you want to do?
So basically, do the reduction because it's deterministic. You can verify it there, and then.
Good, exactly. So you start from an instance of P, you run the reduction, which will create some instances of Q along the way. For all of those instances, you apply the verifier to come up with an answer, and then you go back. Like in particular, if one, whatever, you just let the reduction complete. The important thing is when these instances need proofs, you just let the proof for the verifier of P be basically the concatenation of the proofs of these instances. Okay? Now I'm just saying, like you answer all of the calls of the reduction using the verifier, but then you let the reduction figure out what is the answer to P. If you have like one of those many one reductions, you wouldn't have to go back. But we generally allow these Turing reductions, right? Okay. So okay, let's go back to SAT and three-sum maybe, which is maybe our most interesting example, right? So what we suppose we had a fine-grained reduction from SAT to three-sum, tight in the sense that if there was a faster than into the n squared algorithm for three-sum, it would imply a faster than 2 to the n algorithm for SAT. Well, then if we had a faster verifier for three-sum, it would also imply a faster verifier for SAT, which, as we've just conjectured, contradicts NSAT. Okay, now it's a little bit confusing maybe, but really what this slide is telling us, if you believe in NSAT, there cannot be a deterministic fine-grained reduction from SAT to a three-sum. Okay?
Three-sum is where we have actually been able to use code non-deterministic algorithms to get better than what deterministic would do.
Good. We still have to prove this part. Exactly. We'll get there. Sorry, yeah. At the end of the talk, we'll actually see how this verifier for three-sum looks like. Sorry, yes, that's absolutely correct. Before that, though, we'll have a look at some other cute verifiers. But actually, I'd like to, I'd like to point out some detail, which I guess you've already noticed about this slide, which is these reductions really have to be deterministic. That was important basically because if you would allow randomization, then this does not play very nice with the non-determinism we've used in the previous slide. So a very reasonable question is, could the same sort of framework for barriers also work for randomized reductions, right? After all, randomized reductions is what we are thinking about the entire time. Like typically, we just don't care about randomization. We always use it. Turns out no. Like really, one could strengthen it to randomization. One could just define verifiers with respect to a source of non-deterministic input and a source of randomized input. right? But then, turns out randomized NSAT is just false. So, the hypothesis that SAT requires 2 to the n time if you're allowed to use non-determinism, like co-non-determinism, and randomization is simply false. So it turns out Ryan Williams has proved that in the following communication setup, which again maybe should remind you of what we did in the morning, where the verifier sits in the middle, he holds some KCNF formula phi, and then there's these two parties, right? There's like a randomness, which just stupidly samples some coins and sends them to the verifier, and on the other hand, there's Merlin, who knows the formula and can come up with whatever answer he chooses to help help the verifier. Turns out this, and then the verifier, of course, has to decide whether the formula is satisfiable, right? In this setting, there is a protocol, or basically just a randomized verifier, with the following parameters. So the message size which Merlin sends really has size only 2 to the n half, 2 to the n half bits. And the randomness is ridiculously small, polynomial, okay, that's fine. But the verifier can then also compute whether the formula is satisfiable in time 2 to the n over 2. Okay, so there is a non-trivial randomized verifier for satisfiability, which runs in time 2 to the n half. Yes?
Can you go back a couple of slides? I'm trying to understand what you mean when you say the verifier is both non-determinism and co-non-determinism.
Well, it's non-determinism and co-non-determinism. This is just this, right? You have 2 algorithms, basically. One for the non-deterministic part, one for the co-non-deterministic part. And if you prefer to think about it that way, you can also assume you have the verifier of this kind, which is then just one algorithm, but it can report bottom. Okay? Yes?
So just to check if I'm understanding, you're saying that there's this barrier from that it seems if you believe NSAT, we can't find a deterministic reduction.
Yes, exactly.
But we do randomized reductions all the time.
Yep.
So what's the point? Like.
Yeah, no, you're right. I mean, you can view it that way. I think there's 2 answers to that question. The first one is, turns out for most reductions which we've seen, you can avoid randomization. Actually, for randomization mostly showed up in these 3-sum-based reductions. And for those, we could basically prove that you don't need it. There's 1 or 2 left for which we still don't know, but like the conceptual barrier is not there anymore. The second answer is maybe, but okay, you're right. Even though there might still be a randomized reduction, it would be perfectly happy. But well, you kind of still have to overcome the barrier in there. Like we know this one technique to come up with better algorithms which use randomization and non-determinism at the same time, which is you've seen in the morning. So you guess a polynomial which tells you some answer, and then you use polynomial identity testing. Unless you're able to use that technique, it would still be extremely interesting to come up with reductions. It would still be interesting to break this barrier, even though it's not officially formally broken. Yes?
In the fine-grained setting, randomness will make a big difference, right?
Can you say it again? Sorry.
In the fine-grained setting, randomness will make a big difference, because even if we believe in de-randomization, there might be linear blows, which will be costly for us in the fine-grained setting. Right? So we can't just say that because we can de-randomize almost anything, we believe in de-randomization.
Absolutely.
We believe in fine-grained setting.
No, it's not as black box as maybe for p-vers and like the polynomial time problems is where you maybe can even hope that you can de-randomize completely for free. No, it's just like a heuristic which says for almost all fine-grained results which we know, we could de-randomize so far. Right.
If there is a randomized reduction, it could potentially lead to many different kinds of instances where you would need really different groups.
Sure.
So how do you pull them back kind of?
Good question. I don't think that would necessarily be an issue. I mean, as long as we can boost the error probability of all instances to be very small, like polynomially small, I think it should be fine. Okay, but up to that detour on randomized versus deterministic, this is really the picture that we should follow, right? You prove that for some problem you have a fast verifier, you believe in NSAT, and you can conclude that most likely there's no reduction from SAT to your problem. Okay? So now, assuming that you believe this framework and don't have questions about that, what I'm about to do is we'll go through a bunch of cute small problems and design verifiers for them, just because it's fun to use non-determinism in algorithms. This is not quite what we aimed to do in the first place, so maybe some of the problems are not particularly interesting to study with respect to fine-grained reductions, but still, it's fun. And then at the end of the talk, we'll go back to the three-sum verifier and actually prove that this exists. OK? Good. So simple verifiers. Let's start with the hitting set problem. So it was on one of the exercise sheets. Let me still remind you, though, about the problem. So the input consists of n sets over some smallish universe. Think of D. Same as for OV, you know. Think of D being small. And the output is whether there exists a set Si that intersects all other sets, S1 through Sn. Best known algorithm we know is in quadratic time, which is just, well, you test all pairs of sets, and if you found one which really intersects all, you return this one. Can you think of a faster non-deterministic and co-non-deterministic algorithm? So faster verifier. I'll give you a minute.
If a set is intersecting with, oh no, that's not, sorry.
You have an idea? Give me like 20 more seconds, and I'll ask you. OK. So did you have a complete answer? Non-deterministic and co-non-deterministic?
Yeah.
OK, then let me first ask all the people, can you think of a non-deterministic algorithm? Right? Non-deterministic really just means you have to certify the yes instances of this. Just? Yes, exactly. You just guess the solution set Si. Right? That's mostly the easy part. Often, the non-deterministic algorithm is just trivial. Now tell me, how would you come up with the code?
For every single I, you give the set that has no intersection with that Si.
Perfect. So this would be a no instance, and the co-non-deterministic algorithm would just guess for every set which one, like one other set from which it is this time. Very nice. Let's ponder about it a bit more, right? So what's the time complexity of this algorithm? Well, the non-deterministic one was extremely fast. You just guess the solution, you verify the solution in linear time, maybe n times d. The co-non-deterministic one is also extremely fast. Well, you guessed n bits now, which is way more non-determinism, but the verification is still extremely fast, right? You just have to check for all these pairs whether they're truly disjoint. Still n times d. So we have a much, much faster verifier for this problem than an actual. OK. Next one, Euclidean radius. The input is endpoints, let's say from Euclidean space of some small dimension. The task is to find, you want to find basically a center point and draw a radius around that center point and minimize that radius. So for instance, maybe here you should pick that center point and draw a radius around this. That is like the smallest way you could draw a cycle around these nodes. Question is to compute this radius. Same question. Can you think of a non-deterministic and co-non-deterministic algorithm? I'll again give you let's say half of it.
So for the decision version of this problem,
The what?
if you're saying co-non-deterministic, so for a decision version.
Oh, sorry. I should have just think of a verifier in the sense for verifiers of non-deterministic. Verifying, yes. If you that's another way to think about verifiers for non-decision problems. You just think of the decision version of the problem. But yeah, I don't know. Let's start simple. What's the non-deterministic algorithm? What was that? Yes? Guess the point. Exactly. You guess the center. From this, you can verify in linear time you can compute the radius. What about the other direction? How do you prove that really this is the center point? So how do you give an upper bound on this radius?
On each point, find the farthest point.
Yes. For each point, guess its furthest point. OK, so again, this is like n pieces of information which you guess non-deterministically, or co-non-deterministically, whatever. And then you can verify for each of the pairs what's their distance, and if all of them really are bigger than the distance you have computed in the first step, you know that you work correctly. OK? Are we on the same page? Does that make sense? Good. So maybe you've noticed this. This and the last example were actually pretty similar. There's a general concept behind that. The concept being whenever you have like a quantifier alternation in your problem. Like you first existentially quantify something, then universally. Or first you have like a min and then a max and whatever. Typically you have fast verifiers. Yes? Well, if you think about the verifier, it has to prove to you that the answer is correct, right? So one way of thinking about it is you first, you guess an upper bound on the actual radius. And then to say that there's no better point which you could choose, you can find for every point its furthest point. So this will definitely give you like whatever is the smallest among these will be like a lower bound to the solution, right? OK, next example. Max flow. Right, you've seen it a couple of times now. In the very simple version, right, you're given an edge-weighted graph with some designated special vertices S and T. Task is to compute the flow, the maximum flow from S to T. Now, some of you might just know the answer immediately. Please don't tell us. For those of you who don't know the answer immediately, I'm going to give you like 30 seconds to think about it. Who can see how it works? Not as many as I expected. OK. You want to offer a solution, or you can see it?
A solution.
OK.
For finding mean curves, we have some deterministic algorithms, and mean curve is equal to.
So you're making it more complicated than it is, but the second part is exactly right. Max flow equals min cut. So what should be the algorithm? OK. I think all of you basically agree. First of all, you guess an upper bound on the max flow, which is, well, you compute, I guess it's a lower bound, right?
Yeah.
Lower bound. This should be lower bound. You guess a lower bound by guessing some flow. In this case, the flow would be 16. And then you guess a cut, which is the minimum cut, which has the same value, certifies that the flow you guess is actually maximum. OK? That's fun, right? Final example, linear programming. Suppose you're given, right, a typical input to linear programming is like you have some constraint matrix or whatever. The right-hand side, so that A and B define this polytope. Then you have this direction, and you want to find the point which is furthest in the direction induced by C. How many of you see, given the last slide, immediately how to get a verifier here? OK. I'll give you 20 seconds to think about it, though. OK, any aha moments in the last 20 seconds? Anyone who wants to offer a solution? Yes?
So you can give a feasible solution for upper bound, then look at the dual and give an upper bound.
Nice. Exactly. Yeah, you guess the primal and the dual optimal solutions. You test that they have the same value, and by strong or weak duality, whatever, you get that you have necessarily an optimal solution. Okay, so this is the second sort of family which shows up. The first one was this quantifier alternations. Second one is dualities, which I guess in the most general form, or in a very general form, is for linear programming. It's even more general ones. Okay, so those are somewhat simple. Keep them in mind. Maybe for the purpose of fine-grained complexity, the last one is not as important. For max flow, obviously this is a linear time problem. At least we know now, so it's maybe not as interesting. It is more interesting for variants of max flow. Like there are some, for instance, there's a what is this? Directed, uncapacitated max, all pairs max flow, for instance. Some of these problems are still open, and for those, it is actually interesting to find SETH lower bounds. And then in a recent paper by Ouattara-Belzi, he showed that actually, there are verifiers, so you should not expect lower bounds. The other ones are more interesting. Like, for instance, Euclidean radius and hitting set really are problems for which people have tried to find fine-grained lower bounds. Due to these verifiers, most likely they cannot exist under SETH. So actually what happened is kind of funny. Hitting set just became a conjecture. Now you base the lower bounds on hitting set. OK, anyways. Let me move on. So last part of the talk, and maybe the most technical one, let's talk about the three-sum verifier. But before that, we'll start with some preparation, which you've seen before, because we put it on extra sheet 1. But nevertheless, it's kind of important, so let's recap. So here's an important fact. Degree D polynomials can be multiplied in time d log d. Right? For this, you kind of have to first understand what does it mean to store a polynomial in memory. And by this, let's say you store a polynomial as like its coefficient representation, as like in a length d array. Then there's an algorithm which can multiply two polynomials, like produce the coefficient representation of their product in time d log d. And this is called the fast Fourier transform. It's very, very helpful in the context of three-sum. Appears in a lot of algorithms, a lot of reductions. Just always keep it in mind when you work on three-sum. Good. And then on the Excel sheet, you prove basically the statement, not quite as general, which is you can count three-sum solutions over a small universe very efficiently. And the Excel sheet was about decision. Actually, you can do counting. So the formal statement is, given a set of three-sum instance over universe minus u to u, we can count the number of triples satisfying that a plus b plus c is equal to 0 in time u log u. OK? Anyone remember the proof? Yes?
You can model the frequencies in a polynomial.
Like what?
Huh?
How exactly?
Oh, the coefficient of x power I is just how many times that element appears, and then just cube this polynomial.
Good. So another way to say it is you take this polynomial, right? You just take the sum of all the elements s, x to the s. Tiny difficulty is, well, they can have these s's can be negative, right? So we shift them. Good, exactly. So we come up with this degree 2u polynomial due to these shifts of the form sum of the s and s, x to the u plus s. Then you compute p cubed by calling FFT 2 times, right? P times p times p. And the claim is you can just return the coefficient of x to the 3u in that polynomial p cubed. Right? The reason being, like, whenever you had a triple a, b, and c, this corresponds to some term x to the a plus u times x to the b plus u times x to the c plus u, which, if a plus b plus c is equal to 0, is just x to the 3u. All the others distribute over the other coefficients of that polynomial. OK. So really, you can read off the number of three-sum solutions just from the coefficient here, and you return it. OK. Also, it's very easy to modify this algorithm to also not only compute the number of solutions, but also the number of solutions modulo u. So we also get this statement. So now you're given a set S. Maybe it's of numbers between u and 0 and u minus 1. You want to count the number of solutions satisfying that a plus b plus c is equal to 0 modulo u. Yeah, this is not the proof anymore. You just apply the previous one maybe 2 or 3 times, depending on what is the overflow. OK. Good. So keep this in mind as a tool. Now we get to the fancy stuff. So let's talk about the verifier for threesome. Indeed, what they came up with is there is a co-non-deterministic threesome algorithm running in time n to the 3 over 2. And again, same story, right? I just put co-non-deterministic here because non-deterministic is trivial. You just guess the solution. So really, to come up with a fast verifier, you really only need the co-non-deterministic algorithm. I'm not sure. Does anyone want to offer an idea? I would be extremely impressed if someone can come up with it right now, but yes.
Like guessing the two modulars of size n3 over 2 and do the threesome problem in that modular.
Say it again, please. The first part only.
Just set the modular size of n3 over 2.
Good. Okay, that's already a very, very good start. I like that. So what you're saying is you should hash in some sense. Now, if you remember from the first day, linear hashing, it's a little bit technical, but the idea was basically you can choose a random prime. Well, I guess on the first day we used it for several reasons. One of the reasons on the exercise sheet was you could also use it to reduce the universe size of threesome. There on the exercise sheet, it was to reduce the universe size to n cubed. And then you could actually see with n cubed, you would not introduce false positives. Now what you're suggesting is let's reduce the universe size even smaller. Like reduce it to something like n to the 3 over 2. And this will introduce false positives. It necessarily have to. But let's choose it in such a way that we only have few false positives. OK, so let me call these false positives pseudo-solutions again to be in line with the notation from the first day. So then we want to guess a prime such that there are at most n to the 3 half pseudo-solutions, where a pseudo-solution is solution mod p. OK. Why does such a prime exist? OK, that's correct. This is the formal proof. But just take the theorems you've already seen before. Can you give me a black box answer as to why it must exist? Well, why does such a prime exist? Just pretend that p is random. We assume we sample p at random, and we analyze what would happen. And it turns out, this is the analysis, which I'm sure you remember in detail from the first day. So the expected number of pseudo-solutions if you pick a random prime was just the sum of all triples ABC. What's the probability that ABC becomes a pseudo-solution mod p? Which is equivalent to saying, well, then p divides a plus b plus c. But this probability is simply upper bounded by the number of prime divisors of a plus b plus c divided by the total number of primes in that range. Now we start from numbers which are polynomially bounded in the first place, so every such number has at most log n prime divisors, right? Every prime is at least size 2. You can have at most order log n divisors of size at least 2. And the prime number theorem tells us that there's roughly n to the 3 half primes in that range. And if you work that out, actually, it turns out, indeed, there are at most n to the 3 half up to log factors pseudo-solutions in expectation. That's important, right? We choose a random prime here. But if you can prove an upper bound on the expected number of pseudo-solutions for a random prime, well, then obviously there's at least one good choice. So take that. OK? Damn it. Didn't want to show that. Anyways, good. So the second step is listing. Now we have reduced the universe size. And the strategy these guys came up with is, well, let's just list all the pseudo-solutions. For each pseudo-solution, we can just test whether it is a proper solution. And if we do not have any proper solutions in a list, that's it, right? Then we should easily verify that the solution, that our instance is unsatisfiable. OK? Repeat it once more. Guess the list L of all pseudo-solutions. Verify that L contains only pseudo-solutions, no nonsense, and no proper solution. And OK, no repetitions. So that's it, or you have a sorry?
How do you know you guessed all of them?
Good, exactly. Yes, how do you know you guess all? The verifier might still cheat, right? Like, it might just omit the actual solution from the list. Good point. How do you solve it? Perfect. You count. Use the lemma from the previous slide to reliably count the number of pseudo-solutions. And then you just verify that this count equals to the size of your list. Now, how could you possibly cheat, right? If you omit a number, the verifier will catch it in the step 3 because it'll say, well, you just didn't give me all the solutions. And all other ways of cheating, like maybe you could repeat some solutions. Well, then you have to make sure in the second step that you do not repeat solutions. OK? Questions about this? Very magical, I think. And also a very generic concept. I think you should keep that in mind. Like the hash list and count turns out to be very useful for non-deterministic algorithms. I'm not going to show you the same thing for APSP, though it is known for APSP. So for APSP also, there is a better than cubic time verifier. And we're going to put that in the Excel sheet tomorrow. So you can figure it out by yourself. Oh, by the way, yeah, maybe quickly analyze it, right? So sure, step 1, lens in constant time. We just guessed the prime. Step 2, we said, well, you have to list all the pseudo-solutions. And if you choose the right prime in step 1, there's at most n to the 3 half many of them. And then FFT runs in time proportional to the size of the prime, which is also n to the 3 half. That's how we arrive. Good. OK, let me conclude. So we set out to ask whether there's one conjecture to rule them all. And the answer turns out to be probably not. Which is fine, though. It's like in my being a little bit more philosophical, in my opinion, that also makes a lot of sense. Because while like in the NP hardness world, there really is one reason of hardness. The reason being, you encode satisfiability, which is like the fundamental problem, and just asks, is non-determinism necessary in a way? Like, it just says, you have to brute force somewhat. In the fine-grained world, we have more subtle reasons of hardness. It's not everything is about saying, well, your problem encodes brute force, which is like basically the SETH hard problems. But there are also hard problems which encode, having some sort of arithmetic hardness, or something which has to do with, finding negative triangles, meaning like comparisons. So I don't think it's bad at all. It's just very natural that we have many hardness hypotheses we have to start from. Maybe there is a way to unify them in the end, but even if it wouldn't happen, I think that's still very satisfactory. OK. I think I'm going to stop here. And yeah, this was actually my last lecture. Just one second. So I had a lot of fun. Hope you had too. There's another lecture by Amir tomorrow. So yeah, let's watch out for that. Anyways, thanks. OK, you had a question.
So do we have a verifier for APSP?
Yes, there is a verifier. Sorry, we're going to put that in the Excel sheet tomorrow.
I see.
So you do similarly rule out reductions from SETH to APSP. Sorry?
I just missed that. Of course.
Can
Other
P sum or APSP later?
Sorry?
Can that be a fine-grained solution between P sum with the bypass?
Yeah, that's a good question. I don't think there's anything which rules that out. In fact, like Amir teased it a few days back, right? If you could just invert or prove some better reduction from zero triangle the other way, you might even get it. Other questions? Yes.
Is there an attempt from other hypotheses to SCP?
I don't think so, and that is also there should be like other reasons why that doesn't work. There's a thing maybe you have noticed that maybe you didn't like. All these reductions basically they go from problems with very large complexity to problems with smaller complexity. The reason is often that this direction feels easy because you can just, like for instance for SUD, right? You start from a large search space, but actually the instance is very small. And you can just enumerate some parts of the search space and make this part of the smaller instance. You can blow up instances, what I'm saying. But the other way would be you have to compress an instance. And that is generally, like at least, I mean, we don't know how to prove it formally, but it seems pretty much impossible. Yes?
Does the verifier argument immediately rule out the other directions? So P sum to set
No, it does not. It does not rule out anything in this direction. But as I said before, right? Like informally, this direction seems even more ridiculous than this one.
What about OV? That's the non.
I mean, well, no. If you had a reduction from OV to threesome, in particular, you had a reduction from SETH to OV to threesome.
Oh, no.
Yes?
You have like a less fine-grained reduction from OV where you don't break SSH, right? That's where.
There are some non-tied reductions, yes.
And then you can maybe get some.
Yes, so it's true, like what we didn't show in the picture, you can, in many cases actually, prove some non-tied reductions, but then there's a question, what do they actually mean? I mean, less interesting. Randomized reductions, we still don't have any papers.
Is there a reason why we believe a randomized reduction?
Okay, so I'm lying a little bit when I say randomized reductions don't work at all. There is an hypothesis which is it's called non-uniform, non-deterministic SETH or something, where you basically have, in addition to non-determinism and randomness, I guess you have to.
You don't have randomness, instead you have a circuit.
Exactly. You don't have randomness, but you have non-uniformity. Like you can guess for any advice. You can basically guess advice, which is not exactly the same as non-uniformity. But if you believe that hypothesis, which has no real reasons to believe in it, but if you believe in it, then you can rule out some reductions. I suggest that you check out the paper, this Camazino et al. Paper by the San Diego crew. They write it in detail.
How much of the big picture are you omitting here? Like, are there a bunch of other conjectures?
Oh,
is there like an infinite hierarchy of conjectures?
Yeah, good point. Okay, we do not have an infinite hierarchy of conjectures, at least not one which really matters. We have some more conjectures, like hitting set is often a conjecture. There's, whenever there's like a triangle conjecture, negative triangle for instance, typically there's a clique conjecture about this, and they're very useful to prove reductions. Often there are quantified versions, like for instance for, basically the same as for hitting set, there's also a version of SETH which is quantifier alternations, like it exists for all satisfiability question. And I guess if you really wanted to, you could view that as a hierarchy, but no one does that. We just either, we just call it quantified set, so we jump to like the p-space analog basically. There's some smaller ones in there, though I think like everyone kind of agrees that these are the primary ones and all the other ones don't come close.
Very kind of specific technical question.
Sure.
Does refuting n-set leading to circuit lower bounds have something to do with this algorithms to lower bound framework of Williams? Or
Yes. Yes. Exactly.
Can you explain that?
I can explain that. Let's talk like in person. I think otherwise we're going to miss basically all the people. Other questions? Okay, great. See you tomorrow.